Hi, everybody. Welcome back to Dave's Math Channel. This is my continuing feature on the Math Lovers book. And a couple days ago, I started a new chapter, Chapter 7, which is on logic. And a big part of logic is Boolean algebra, which I started yesterday. One very important construction in Boolean algebra is truth tables, and I'm going to spend the next couple lessons talking about truth tables. This is the first one of two. So anyway, let's begin. So I think I'll just start with a simple example. Remember last time I talked about Boolean operators, or there's three of them. There are three commonly used ones: and, or, and not are the three most common Boolean operations. And not is the simplest one because it's a unary operator, whereas and or are binary. Unary just means it operates on just one variable, one Boolean variable, which I'm calling P here. And I'll get into and or after this. Those involve two variables, so those are binary operators. But what the truth table for not looks like, on the left we have our variable P, in this case just one variable, and it can have two possible values. Every Boolean variable has only two possible values, namely true or false. True I'm symbolizing as T, and false as F. Some authors use 1 and 0 instead. That's more commonly used in computer science, because computers use numbers, binary numbers, and 0 stands for false, 1 stands for true. But here I'm using true and false because it's a little more like English and a little easier to follow. I'm going to give some examples of some logical arguments. I just think it's a little easier to work with T and F. So anyway, so for instance, P can represent an atomic statement, like I'm a mathematician. That's true. And so P in this case would be true, and its negation would be the negation of the statement I am a mathematician. That would be I am not a mathematician. Either I am a mathematician or I'm not. And it's always the case that if a statement's true, its negation is false, and vice versa. So since I am a mathematician, that's true, and that means the statement I am not a mathematician is false. So that's a simple example. But then P could also be something that's false. For instance, P could be the statement I'm a football player. That's false. I'm not a football player. My dreams, maybe. But anyway, the statement I'm not a football player is false, but the negation of that would be I am a football player. And that is, oh no, I'm sorry. The statement I am a football player is false. The negation of that is I'm not a football player, and that is true. I'm not a football player. So I think you get the idea. The negation of a true statement is false, and the negation of a false statement is true. That's all this truth table says. It's just how the logical operation not works. It kind of defines the operation. And then the next two more complicated Boolean operators are and or. And is also known as conjunction. And if you remember from yesterday, the symbol for and is this upper wedge. It looks like an A without the horizontal line through the middle. That's an easy way to remember it, A for and. So now, since and is a binary operator, that means on the left side we have to have two. It acts on two Boolean variables, which here I'm calling P and Q. And by the way, the convention for variable names for Boolean variables usually start with P. You go P, Q, R, S, and so on. Whereas for I guess numerical variables, people usually use X, Y, Z. It's not an absolute convention, but it's a convention I use. So anyway, now there's four possibilities because we have two Boolean variables, and that means that P can either be true or false, and Q can either be true or false, and we have all four possible combinations of P and Q, namely true, 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 false, false, true, and false, false. In general, if we had n Boolean variables, we would have 2 to the n columns. So for instance, if we had 3 Boolean variables, we'd have 8 columns in our truth table. if we have 4 Boolean variables, we'd have 16 and so on. I don't think I've ever seen a truth table with more than 4 Boolean variables. They get very difficult to work with beyond that. But anyway, so now let's just start with some examples. I think it's easier to start with concrete examples. Say B is the statement, the sky is blue. Well, that's true, unless it's overcast. Let's assume it's a clear sky, then the sky is blue and it's daytime. And then Q can be the statement 2 plus 2 equals 4. That's obviously true. And what this truth table says, it says how and works. So if we have two statements that are both true, then their conjunction is also true. And I think that should make sense, because the statement the sky is blue and 2 plus 2 is 4 is true. As long as both parts of the statement are true, the conjunction is true. But then if either part is false, then the conjunction's false. For instance, if P is true and Q is false, then P and Q is false. That would be like the sky is blue and 2 plus 2 is not 4. That's false because 2 plus 2 is 4. And then the third column, if P is false and Q is true, for instance, the sky is not blue and 2 plus 2 is 4. Well, since the sky is blue, the statement the sky is not blue is false, but 2 plus 2 is 4. But still, the conjunction's false because it's false to say the sky is not blue and 2 plus 2 is 4. And finally, I think the fourth case is the most obvious one. It's false. If both P and Q are false, then the conjunction's still false. For instance, the statement the sky is not blue and 2 plus 2 is not 4, that's false. Just remember that two wrongs don't make a right. So anyway, that's how conjunction works. And then very similar to conjunction is disjunction. This is or. And remember what I told you yesterday, that and is like intersection. And is like intersection, which is usually like a upward horseshoe symbol. And or is like union, which is a lower horseshoe symbol. And these V symbols are very similar. They open the same direction as the horseshoe. So that's kind of an easy way to remember them. And they behave like intersection and union, respectively, in terms of set theory. Just remember that and conjunction is exclusive. A conjunction, it doesn't have to be just two things. A conjunction of n atomic statements is true if and only if all of them are true. So that's exclusive. Whereas and it doesn't have to be just two things. If you had a disjunction of n atomic statements, then that's true whenever at least one of them is true. It's only false if they're all false. So that one's inclusive. And if you remember how unions and intersections and unions work, it's kind of similar. Take the intersection of a bunch of sets. That's just the stuff that's common to all the sets. And the union is the stuff that's common to any one of those sets. So in terms of set theory, or is like union. Anyway, so that should make this truth table kind of easy. So now the way or works is that P or Q is true whenever at least one of P or Q is true. So for instance, for this case, that would correspond to the first three columns of this truth table, because if P and Q are both true, then obviously it's true that P or Q is true. For instance, the sky is blue or 2 plus 2 is 4, that's true. And whereas for the second and third columns were false, for this case they're true, because only one of them has to be true. The sky is blue or 2 plus 2 is not 4. Well, the or doesn't care about the second part, which is false, so that statement's true. And similarly, the sky is not blue or 2 plus 2 is 4, that's true as well. Because 2 plus 2 is 4, and that part, once you have that part, you don't care about the false part. The sky is not blue. But the case where they're both false is still false. It's still false to say the sky is not blue or 2 plus 2 is not 4, because both parts are false, and so the disjunction is also false. Neither of them is true. So that's how or works. So those are the basic Boolean operations and their truth tables. But you can make more complicated ones, and there's a lot of other useful ones. And I'm defining 3 more. I think I talked about these yesterday. So it's useful to define some other Boolean operators besides and, or, and not. I mean, and, or, and not are functionally complete. As a matter of fact, like I mentioned yesterday, and not, or and not are functionally complete. But it's useful to have more. There's a lot of logical arguments where it's useful to use more complicated operators. So here I'm doing three other ones. And implication, if P then Q. That's the arrow going to the right. And then equivalence, P with the three lines, P is equivalent to Q. Sometimes people write this as a double arrow, arrow with a arrowhead going to the left and to the right. I prefer writing it this way. And then we've got exclusive or, which we write as a plus sign with a circle. So this truth table shows you how each of these three more complicated Boolean operators, and they're all binary. So we have 4 rows like we did for or and an or. But this truth table shows you how each of these logical operators work. Let's start with implication. If P then Q. So people usually say this is if P then Q. Well, if P and Q are both true, then it's true that if P then Q. You can kind of think of this as a definition. The only case in which if P then Q is false is if P is Q and P is true and Q is false. I mean, that should make sense to you because there's implication going on. So what implication kind of means is that whenever remember the thing on the left is usually called the premise or the antecedent, and the thing on the right is called the conclusion. And you can kind of think of this as a cause and effect thing, like if I drop my phone from the air, it's going to fall. Yeah, that's a given. That's the law of gravity. So one way you can think of that is, if we assume that we drop the phone, then obviously it's going to fall. It can't be the case that I drop the phone and it doesn't fall. The law of gravity forbids that. So that's the only case that's false here. I think the first case is pretty clear. I mean, that is just what it's saying. You do the thing on top, and then the next thing follows. The ones that are controversial and are the third and fourth columns here. By convention, they're both given the truth values true. And a lot of people don't like this. When I first learned this, I didn't really like it either. I mean, they're kind of meaningless if you think about it. When P is false, then you really can't conclude anything, right? So the law of gravity says if I drop my phone, it's going to fall. What if I don't drop my phone? The law of gravity doesn't say anything about what's going to happen in this case. So I think by default, people just write true because it has to be something or other. And I guess by default, true is more a nice default than false. But, maybe it should be undefined. I don't know. It just makes logic a lot harder to work with if you make them undefined. So by convention, we make them true. But I know a lot of people don't like this convention. And it is just a convention. So I think that's probably the most controversial definition that I've seen anyway in Boolean algebra that makes things consistent. And what about the second of these, the fourth column here, equivalence, logical equivalence? This one I think is more straightforward. Logical equivalence just means P and Q have the same truth value. It says P is equivalent to Q. And maybe I can think of a good example of that. So the implication goes in both directions, and that would be kind of like a tautology. Like if I'm single, then I'm a bachelor. I mean, they're synonyms, right? So that means that if I say I'm single, then I'm obviously a bachelor. If I'm a bachelor, I'm obviously single. They're the same thing. So that means that it can't be the case, if one of them's true, the other one's necessarily true. And if one of them's false, the other one's necessarily false. Another way to say that is the implication goes in both directions. So sometimes you do get double implications. I gave a pretty obvious example where it's just a synonym, but there's other double implications that aren't really synonymous. They just work in both directions. Maybe you can think of some. And then the last one here is exclusive or. I think I talked about this one last time too. And this is actually the opposite of double implication. Uh, or equivalence, logical equivalence. Remember, exclusive or, the only way it's a little different from regular or is that it's like A or P or Q, but not both. So, for instance, if P is true and Q is false, it's true. If P is false and Q is true, it's true. But in the case of regular or, if P and Q are both true, then P or Q is true. But here we're saying exclusive or. That means P or Q, but not both. And sometimes people do use or in this context. So anyway, this is the truth table for it. If P and Q are both true, then P exclusive or is false. Then also if P and Q are both false, then neither of the parts are true, so the whole result's false. So that those are the truth tables. That's the truth table for implication, double implication, or equivalence, if you like, and exclusive or. And I believe that completes my lesson for today on truth tables. I'm going to do another lesson on truth tables. I'm going to talk about how we can use them to actually prove statements. Anyway, I'm done for tonight. So thank you for watching. Long live math, and I'll see you guys next time. Bye.